Okay, so let's look at this first problem right here. It says write a function v of h that represents the volume of the planter box. So I'm gonna fill in some things up here in the table. The height is represented by h here, and then the width, okay, is gonna be right here, 18 minus 2h, and the length is actually gonna be this little section right here, which is 12 minus 2h. And then it's asking us to find the volume, so we have to do the length times width times height of a cube. Okay, so we're fixing to multiply all these three right here, length times width times height, okay, and then we'll work it out. So we're gonna say v of h is gonna be equal to these three multiplied by each other. So we have h times 18 minus 2h times 12 minus 2h. Okay, now I have three terms that I need to multiply by. And so what I'm going to do is I am going to just take two of them at a time. So what I'm looking at is h and this term. And so I'm going to FOIL that out first, or distribute. And so that's going to give me 18h minus 2h squared. All right, and then all I'm gonna do is I'm gonna drop down this, and then I'll multiply all this out as well. I'll FOIL that out. So then I do 18 times 12, and that gives me 216h, and then I do 18h times negative 2h, which gives me negative 36h squared. And then I do this negative 2h times 12, which gives me negative 24h squared. And then this negative 2h squared times the negative 2h squared, which gives me a positive 4h cubed. Okay, notice we do have two like terms here. So I'm going to combine those, and I'm going to kind of rearrange this in standard form. So what we want is the one with the highest exponent first. So it's going to be 4h cubed. I'm going to combine 36 or negative 36 with negative 24. And I'm going to get negative 60h squared. And then I still have this plus 216h. So now this is written in standard form. So this is what it wanted us to get to. Okay, and so this is going to be the table that I use to kind of figure out what's going on. So here I have this table, and what I'm going to do is fill out the rest of it. So it wants us to know the width if the height was 1, the length when the height was 1, and so forth, right? So all I have to do is input 1 for h in both of these. So if I input 1 here, it's 2 times 1, which is 2. 18 minus 2 gives me 16. If I input a 2 in for h, 2 times 2 is 4. 18 minus 4 gives me 14. And then a 3, 2 times 3 is 6. 18 minus 6 gives me 12. And then you kind of see the pattern. It's just going down by 2 each time. And then I do the same thing with the length. I input 1 for the h, 2 times 1 is 2, 12 minus 2 is 10. I input 2, 2 times 2 is 4, 12 minus 4 gives me 8, and again you see a pattern here, and they go down by 2 each time. Okay, and so then to find the volume, all I do is multiply these three numbers, 1 times 16 times 10. I've already done the work ahead of time, so this gives me 160 cubic inches. The next one is 224 cubic inches. 216 cubic inches. 160 cubic inches. 80, 0, and negative 56, all cubic inches. And so we look at our table here, volume, and things stick out right here. We do not have a reasonable answer for these two, so these two are unreasonable because we can't have a zero volume or a negative volume, so unreasonable. So what we're really looking at is anything kind of from there to there. All right, so then I'm gonna go and continue on to the rest of the page. And so I'm gonna be kind of flipping back and forth between the paper and this context versus what it looks like on the calculator. So it wants us to enter in the equation that we found earlier into our calculator. I've already done so in my calculator, so if you need some time, just pause the video. I also inputted 0 in Y2 because we are going to find the zeros, or I'll show you how to find the zeros on that for what's going to be on page 2. So if I look at my graph, first I go to the window and I'm going to adjust it to -10 and 15 for the X min and X max, and then -400 to 400 for the Y min and Y max. And when I go to my graph, you should see something graphed like that on the calculator, okay? And so if I'm just looking at this graph, so then we kind of look at what A, B, C, and D are asking. So if I'm just focused on this graph alone and what I see on this graph, if I were to ask you what the maximum was, then you guys would probably say it heads into infinity, right? So I have to understand the context of this problem. So when I look at this, we have, it does approach infinity right here, but with the context of our volume, we're only going to be a maximum at this top point right here. This is called the relative maximum. And so if I wanted to find the relative maximum on my calculator, I would just find the maximum. I would still hit second trace 4 for maximum, and then I would move this cursor to the left of that point right there, hit enter, move it to the right, hit enter, and then hit enter one more time for your guess, and this will give you the ordered pair for the maximum or the relative maximum. Okay, so if I was just looking at my table, okay, then my maximum of my table would be right here at this volume right here, 224. So that's what we're going to kind of write down based off of what's on our table, okay? So this is what's the maximum volume. You know, we'll just put from table, and that gives me 224 cubic inches, okay? So that's the maximum volume that we have. What are the dimensions for that planter box? The dimensions for the 224 cubic inches were 2, 14, and 8. So just 2, 14, and 8. Okay, were my dimensions. Now, again, part B, it says what is the domain of the function? So when it's stating the function, it's referring to the equation, our calculator. So if I look at my calculator, this domain, how far left to right, okay, the domain would be -infinity to +infinity, right? If I were to find the domain in the context of the volume problem, then really I just need to look at my table right here, and I look at what's reasonable, right? So my domain started at 1, and then it became unreasonable at 6. Okay, so that means it's still reasonable at like 5.5. And so in the context, okay, the domain here would be 1, sorry, it can be equal to 1, so we use the bracket, to 6, where it cannot be equal to 6 because that's when it becomes unreasonable, okay? So these two domains are not the same, okay, because the context of the problem is just 1 to 6. So if I'm answering this question, I would just put no, okay? And then we do the same thing for the range, okay, how low to how high. So -infinity to +infinity is the function. Okay, is that the same as the context of this problem? No, because I look at my table and I look at the lowest value, which I got is 80, and then the highest value, which I got at 224. Okay, so again, the answer would be no, they are not the same, okay? And then it says, what do the x-intercepts represent in the situation? So x-intercepts, this is where I did in y2, x equals 0. And then we just find the intersections the same way we have in the past. Second trace 5, and then move the cursor close to the one that you want to find and hit enter 3 times. So this one has 3 times that it hits 0 at this point, which is 0, 0, at that point, and at that point. So again, we're just going to do x equals, we're going to open our brackets. The first one is 0, and then I can do second trace 5, intersect again, and then I just move that closer to the second one. Again, enter 3 times, and then we get 6 for that one, and then 9 for the last one. Okay, and it says, what do the x-intercepts represent in the problem situation? Well, all that it represents is that the volume, right? Here's when h was 6, right? The x-intercept, the height was 6, we had a volume of 0. So these are basically going to give a volume of 0. Okay, and then again, we talked about the relative maximum and the relative minimum. So if we just kind of redraw this graph that we have, kind of looks something like that. This is the relative max, and this is the relative min. Okay, so still that low point of that curve.